Welcome to Lecture 12 in General Relativity. Finally, we have reached the point of beginning our discussion about the metric. Although I think we're still n-dimensional here. So really, properly speaking, the metric we're interested in general relativity is for four-dimensional space-time. So I think we're still a little bit needlessly general in this talk, but anyway, let's get to it. So given a manifold M, we say G is a metric on M if G is a smooth assignment of a symmetric type 0-2 tensor, which is non-degenerate at each point. That is to say that G has an expansion is like G mu nu contracted against dx mu tensor dx nu. And here, G mu nu is equal to G nu mu, and the determinant's non-zero. That's the non-degenerate condition. So the inverse of this set of numbers as a matrix is typically denoted G upper mu nu, and so in particular that means that if we contract over nu like this, we get the Kronecker delta with the free indices mu and alpha. Now, the pair of the manifold paired with the metric is just called a semi-Riemannian manifold. Now, I guess I should warn, sometimes I suppose in mathematics metric has a more rigid meaning in terms of it has to be a positive definite symmetric bilinear form. So in other words, for a good part of mathematics, we don't study a semi-Riemannian manifold. You just study a Riemannian manifold. A Riemannian manifold is just one which the is essentially a generalization of the dot product locally for tangent spaces and such. But anyway, let's move on here. More about that as we go. So just a little bit of linear algebra here to sort through. So if we let G be the matrix of the metric for discussion's sake, then linear algebra tells us that the determinant of G is the product of its eigenvalues. And this is true whether G is diagonalizable or not. But in this context, since G is actually symmetric, we can say more. In particular, we can say that since G is symmetric, the real spectral theorem applies, and as such, you can find an orthonormal eigenbasis, let's call it V1 through Vn, for which, so what that means is, of course, that GVI is lambda I VI, and that the dot product of any two of them is either 1 if they're the same, which says it has length 1, or it's 0 if they're not the same, which says they're perpendicular. So in total, then that's orthogonal and normalized, which is to say orthonormal. So this is the real spectral theorem. And but then you can go a step further, and if you take the eigenbasis and you rescale it by 1 over the square root of the absolute value of the eigenvalue, in other words, define a new basis, Wi, which is like that, then if you calculate, let me just get to it here. Let me put all the cards on the table here. Come on. So it's kind of, we've gone from, it was 75 on Friday. Now it's like 45 at the moment. I need to bring this table inside, but my wife is painting and she uses the hairdryer every so often, so it's got to wait. Anyway, so where was I? Oh yes. So if we do Wi transpose GW J, well, we get square root of divided by the square root of the absolute value of lambda I, square root of the absolute value of lambda J, and then of course we've got our Vi transpose GVJ, which since these are as an eigenbasis, that simplifies down to lambda I, lambda J, delta IJ. And if you look at this, it's either 0 if I is not equal to J, or it's lambda I over the absolute value of lambda I if I equals to J, right? And that expression right there is either plus or minus 1, because remember, none of the eigenvalues can be 0, because if the matrix is invertible, the determinant, in other words, the determinant's non-zero, the determinant's the product of the eigenvalues, so none of the eigenvalues can be 0, right? So what that means then is that lambda over the absolute value of lambda, it's always plus or minus 1. And if we arrange the the eigenvalues, the spectrum in order, in terms of increasing eigenvalues, well, at some point you got to cross 0 and go from the negative ones to the positive ones. And as such, with my current nomenclature, the W transpose GW would be a diagonal matrix with minus 1s down the diagonal and then 1s down the diagonal. You'd have s-fold copies of minus 1 and n minus s copies of 1. And in this case, the metric is said to have signature s. So our usual context, like the Minkowski metric, is a signature 1 metrics because we have s equals 2, just to 1. Like this is exactly eta. If you put, minus 1 and then 1, 1, 1, that's eta. And so this whole discussion here has been known for some time. This goes back to the 19th century mathematician Sylvester. This is for reasons that I think are partly lost in history, known as Sylvester's law of inertia. So, some of these calculations you'll see as a physics major, you run into these when you're diagonalizing the moment of inertia matrix. Or I guess we just call it the inertia tensor. But anyway, so remark. In our application of semi-Riemannian, I'll get it right here eventually, guys. Let me zoom in just a bit. Whoop, whoop, whoop. Come on, there we go. So, in our application of semi-Riemannian geometry to general relativity, we study a four-dimensional manifold with the signature of, let's say, minus plus plus plus, which is to say s equals to 1, n equals to 4, so. And by that I mean that there exist coordinates at each point of the spacetime manifold for which you can form the matrix of the metric to actually be eta, right? But generally we don't expect that the matrix of the metric is eta, and we'll soon see it's not possible to restrict G such that the matrix, if the metric is eta for all p in some neighborhood of p. On the other hand, it is possible to select a non-coordinate basis for which the matrix with respect to that non-coordinate basis is eta. Now, I might be wrong about this. It seems like if that's true, then that's true. I mean, I said this. I haven't really, though. I think that this sentence is wrong. It's not possible to restrict G such that for all p. Let's not say some neighborhood. Let me dial that back a bit. It's not possible to restrict G such that, well, no, I just think that that's incorrect. I think we'll soon see that it is possible. Aw, man. All right. Well, let's just keep crossing out. Okay, there we go. It is possible to select a non-coordinate basis, E1 through En, near P, for which G, EI, EJ is eta IJ. All right. What I'm saying is it may not be possible to make that happen for EI and EJ being the partial xi or partial xj. So you can make things happen for the metric with respect to a non-coordinate basis that you maybe can't for a coordinate basis. But anyway, what do I mean by coordinate and non-coordinate basis? We'll be talking more about that in future lectures, not so much in this one, but here let's just make sure we're clear about the meaning of terms before I go on. If V is a vector field, all right, on M defined and on U, a subset of the manifold, and V is a coordinate vector field on U, right, meaning it's a smooth assignment of a vector at each tangent space in U. Tangent space to P for each P in U, I should say. And if there exists a chart, U comma X, for which V is equal to partial xi for some choice of I, somewhere in 1 to n, then to say that E1, I mean, that's what it means to be a coordinate vector field. A coordinate vector field is a vector field that at least locally can be realized as the derivation with respect to a coordinate, right? The derivative with respect to the coordinate. And to say that you got E1 through En, a non-coordinate basis for M on U, is to say that there does not exist a chart, U comma X, for which E is partial xi for I equals to 1 to n. And sometimes a non-coordinate basis is also called an anholonomic basis. which is part of a larger story of so-called anholonomic constraints versus holonomic constraints in classical mechanics. All right. Anyway, let's move on here. So let's talk about some induced metrics on submanifolds. So I guess one of the things I haven't written down, but it's worth mentioning, is that given a manifold and a Riemannian manifold, I suppose. Oof. Yeah, there. You know what? Now I got to mention. I actually I'm not so sure what the status of this theorem is for semi-Riemannian manifolds, but for a Riemannian manifold, I know that if you have a Riemannian manifold, it is possible, all right, to view that Riemannian manifold as being a subset of R to the power n sufficiently large. It can be viewed as a subset of Euclidean space, where the metric on the manifold as an embedded submanifold of Euclidean space is the restriction of the regular Euclidean metric. So, in other words, there's this theorem which essentially says what I'm about to show in the next page or two is very general for Riemannian manifolds. In fact, many Riemannian manifolds could be viewed as a subset of Euclidean space with the metric suitably restricted. These are John Nash's embedding theorems. A weaker form of that was discovered earlier by Whitney. Whitney discovered that you can at least look at manifolds as subsets of Rn, whether or not, for n sufficiently large, right? Sometimes we'll come across like a three-dimensional space which you can't embed in, 3 dimensions. Maybe you can't even embed it in 4, but 5, maybe you could embed it in 5 dimensions, something like that. Don't ask me for an example. I think the Klein bottle is an example, but I can't remember the dimension of the Klein bottle. I think it's, goodness gracious. It might be 2-dimensional, but you can't embed the 2-dimensional Klein bottle in R3. You have to go to R4. So the versions of the Klein bottle that you'll see in 3 dimensions have self-intersection, but those testify to the fact that it's not really a proper embedding in R3. But anyway, my point to you is just that what I'm doing here is what I'm about to do here for the next page or two is relatively simplistic and not as abstract as the concept of a manifold, right, which is an abstract space, right, with coordinate charts, and an abstract semi-Riemannian manifold is an abstract space with coordinate charts, and this type 0, 2 tensor with smooth assignment of that over the whole thing. It is nevertheless the case that there are theorems which suggest that maybe it's possible to view our abstract ones suitably reformulated in this fashion. So, I don't know. That's something. Again, I don't actually, now that I'm making this video, I don't actually know what the status of the analog of Nash's theorem for semi-Riemannian geometry is, if that's an open question, or how closed that question is. I don't know. Or I hope I'm not wrong. I hope it wasn't just that Nash did the semi-Riemannian case. I don't think so, though. Okay, anyway. And now for a few examples from Riemannian geometry inside R3. So basically in R3 we have the Euclidean metric is dx tensor dx plus dy tensor dy plus dz tensor dz. And a shorthand for that is just dx squared plus dy squared plus dz squared, right? And that's a perfectly good shorthand as long as you understand what it means. This is the standard Euclidean metric on R3, and it can be converted to cylindrical or spherical coordinates simply by substituting the coordinate change formulas and taking appropriate differentials. Like here is the cylindrical metric, if you will. Well, this is, I suppose, what I have is for R2. All right, fine. I think I need to let me just put it all out here. Here it is. Here it is. Let me just get it all out in front of us. All right, so there's the formulas for cylindrical coordinates related to Cartesian coordinates. If I take the differential of dx and dy like that, and I tensor them and add things and cancel things, I will end up with, you know, a couple of sine squared plus cosine squared being 1, and I get a ds tensor ds, and an s squared d theta, and of course I also get dz is dz. So here's the Euclidean metric in Euclidean and Cartesian coordinates. Here's the Euclidean metric written in cylindrical coordinates. And while I'm not going to derive it here, maybe I'll make this a homework problem. Ha ha ha. Here is the metric written in spherical coordinates, where I'm using kind of this is somewhere between the typical math and physics notation. My bad, I don't know. So I'm using r for the spherical radius, and I'm using, you know, theta and phi as pictured there, right? So phi is, I think, the so-called polar angle, and theta is the azimuthal angle. And I guess typically in math we use rho equals to r, but anyway, if you take the differentials of these and you know, take dx tensor dx plus dy tensor dy plus dz tensor dz, a bunch of stuff cancels, and it comes back to this. All right. So we can use these to build metrics on submanifolds. Let me show you how. It's really pretty simple. You really just substitute more or less. Like here's one. If I'm looking at the two-dimensional submanifold of R3 given by z equals to z naught, right? So I might call this a horizontal plane. Well, then xy serves as a coordinate chart, and basically dz is 0 on such a plane, and so the Euclidean metric restricts to just dx tensor dx plus dy tensor dy. In other words, h equals dx squared plus dy squared serves as the induced metric on M. Simple as that. All right? Simple as that. Example 2, a little bit more adventurous here. I looked at a plane, right? Here is the plane defined by a times x minus x naught plus b times y minus y naught plus c times z minus z naught equal to 0. All right, and so that's the plane with normal ABC. You take the differential of the plane equation there, right? And you get a dx plus b dy plus c dz equal to 0. And so if a is not equal to 0, just for the sake of specificity here, then you can solve for dx, right? And what that means is that you can write x as a dependent variable of y and z, which means that we can use y and z as coordinates on the plane, actually. And as such, I trade my dx for this and take dx tensor dx, and it gives me back all this jazz right here. So you've got your dy tensor dy, your dz tensor dz, and then you've got the piece which is appearing from dx tensor dx, because x is in terms of y and z, so you end up with a b squared over a squared from these guys, and you end up with a c squared over a squared from those guys as you FOIL this out. And of course you also have this other piece over here, which is minus bc over a squared dz tensor dy tensor dz plus dz tensor dy. And I think for this kind of example, it is worth writing the tensor because it really, I like writing the tensor because it explicitly shows that this mapping is symmetric. It's a symmetric bilinear map, and you can see the symmetry manifestly here, and the fact that you have to have dy tensor dz and dz tensor dy like that. Anyway, moving along here, next example. This one's pretty simple. In fact, most of my favorite examples are formed in this way. You've got a cylinder, so the cylinder is formed by freezing the radial coordinate in the cylindrical coordinates, you know, s equals to s naught. So then ds is ds naught, and what you're left with then, of course, is theta and z as your coordinates. And so the Euclidean metric restricts to s naught squared d theta tensor d theta plus dz tensor dz. And here I'm using what I had on page 3, right? I'm basically using what I had on page 3 with, you know, this right here. I'm just basically, well, that's 0. You're just left with these pieces. And s is in a variable now, right? S is fixed to be s naught, which is the defining radius of the cylinder in question here. And so you could say that this manifold here is a cylinder of, right circular cylinder of radius s naught. All right, so these are examples that we can use as we go on in this course, and Hopefully they'll be useful. I don't know. We'll see. Let's see here. Up next, in a similar vein, sorry, I just put away my page 3, but this is again based on page 3. So if you take the Euclidean metric written in sphericals, and you freeze out the azimuthal angle here, phi, the polar angle, phi, then d phi is 0, so you're just left with these two terms in the spherical metric. And again here, phi naught characteristic of the cone. And yeah, there it is. Oh, interesting. One of the things you might think about here, which is kind of a quirky thing, if you put phi naught equal to pi over 2, then this just becomes dr tensor dr plus r squared d theta tensor d theta. In other words, you could look at this as being the polar metric on the plane if you put the phi equals to pi. Like the cone becomes like a plane, the xy plane, if you put phi equals to pi over 2. It's kind of funny. Of course, there's a little bit something, a little fuzzy there at the origin, I suppose. But then again, polar coordinates aren't really coordinates at the origin either, because coordinates have to be 1 to 1. And what's the angle of the origin exactly? See, we call polar coordinates in calculus 3, but that's really an abuse of the technical language of coordinate in manifolds, if you want to look at it sort of backwards, looking back on it. Now here, and the same is true for this cone. Like I said, that this is a manifold defined by phi equal to phi naught, but it's not really a manifold, because if you look at the matrix, right, of this metric, we get this, and well, the determinant is proportional to sine squared phi naught, and if sine squared phi naught's, well, different things could happen here, right? Like certainly if we had, well, I guess if we have phi naught equal to pi, then we're probably not really. That's also a problem. That would not be a manifold at all. But suppose phi is not equal to 0 or pi, right? So this is a genuine cone. Then still, at r equals to 0, the determinant's 0, right? So there is, and it's not, okay, so like, in the case pi over 2, I would say that that's a coordinate defect, right? If you think about pi over 2, this is just, giving you the plane, the xy plane, right? So for pi over 2, the defect at 0, I would say, is a coordinate defect, in the sense that it's not really present in the manifold itself. It's an artifact of using coordinates which aren't really coordinates at one point. But on the other hand, when phi naught is not pi over 2, right, for interesting angles, right, acute or obtuse, the cone is a cone, and it's genuinely two-dimensional, except for one point, that cusp point, the pointy part of the cone is the place where it stops being two-dimensional. All right, like there's not a nice bijection between the point of the cone and a little neighborhood of R2. So that's the singular point, and that's reflected in the math here. Anyway, fun fact, a space which is a manifold except for a finite collection of singular points is known as an orbifold. So a cone would be a rudimentary example of an orbifold. Lots of fun things have been done in string theory in the last 20 years with orbifolds, none of which I fully understand, but I can tell you this. There is sort of a slogan, which is that singularities are charge, or singularities are topology, something like that. And you can use the orbifold, the degenerate points in the orbifold are exactly the points where physics enters in. And so they tie interesting symmetry groups to those defects, and in so doing build standard model symmetries into branes and things like that. At least they were doing that when I was in grad school. I'm not sure what the state of the art is at the moment, or if all of that has fallen into disrepute, as I have not read the 30,000 pages of string theory that's come out since I've been a professor. Go figure. Anyway, so anyway, here we go. Sphere of radius r equal to r naught is dr equals to, so here you have the differential of r is 0, the spherical radius is 0. And again, by specializing spherical coordinates and freezing out the dr term, you just get, r naught squared d phi tensor d phi plus r naught squared sine squared phi d theta tensor d theta. And so I would say, sidebar, sometimes this is sort of not so much in this context, but in a larger context, this might be denoted like r naught squared d squared omega, where that's the solid angle, and the solid angle over a sphere is 4 pi, for example. But anyway, that's not really for this course, just a passing comment there. All right, so yeah. All right, so let's move on. What's my next example? My fingers are starting to get numb. It's kind of cold out here. So let's talk about how to construct new manifolds from old. All right, so here we go. Suppose you've got M1, G1, and N2, G2 are semi-Riemannian manifolds of dimensions m and n respective, with metrics G1 and G2 respective. Then the Cartesian product of m and n is a manifold with metric basically formed by the direct sum of G1 and G2. In particular, here's the formula. If I take, a pair of vectors, one from m, one from n, and another pair of vectors, one from m, one from n, then I can calculate the metric with respect to that pair of vectors by adding the metric for the first pair plus the metric for the second pair, taken respectively with metrics for m and n, respectively here. In particular, I should also mention, how do you actually form this? How is this a manifold, right? This is a manifold if you use the product of the charts in the natural way. So you take a chart on m, you take a chart on n. The chart on the Cartesian product of the domains for the chart is given by just pairing the coordinate charts for m and n respectively. And so, in other words, in short, m cross n is a new manifold of dimension m plus n. So there's that. And so this construction, right, it allows us to combine two-dimensional manifolds to create a four-dimensional manifold. And so in order to get the kind of four-dimensional manifolds I'm interested in, let me talk about two-dimensional Minkowski space. So two-dimensional Minkowski space, or space-time, or perhaps I should say time-space, it's R2 with a global chart, Tx, right? And again, I'm putting c equals to 1 here because it's fun to be lazy. And the Minkowski metric is this. If I take two-dimensional vectors, like so, and I feed them to the Minkowski metric, then out pops minus v0 w0 plus v1 w1. And which is to say that in the global coordinate chart, which we typically use in two-dimensional Minkowski space, the metric tensor is just minus dt tensor dt plus dx tensor dx, which is to say that the matrix in fact the matrix of this metric in the coordinate basis is exactly the two-dimensional eta, right? Minus 1, 0, 0, 1. So to me, that's just two-dimensional eta, if that makes sense to you. Now, so with all of this in mind, we can create a four-dimensional semi-Riemannian manifold. By the way, my examples up through now, like up through example 5, setting aside the orbifold one, I set aside the cone, or anyway, suitably restricting the cone, let's say that. All of those were Riemannian manifolds because the metric was, what had positive eigenvalues only. They were positive definite metrics, actually. Now these two are not. These are genuinely semi-Riemannian metrics because these have an eigenvalue of minus 1. If the matrix is diagonal, then guess what? The eigenvalues are on the diagonal. So this matrix metric here is a matrix with eigenvalues minus 1 and 1, actually. All right, so signature is 1 for this one. And I haven't written that stuff out, but perhaps I should have. If you look at the, maybe I can fit it in here. So the matrix of G with respect to the natural T, X, phi, theta basis, the matrix looks like what? Oh man, my fingers are so cold, this isn't going to work out well. Minus 1, 0, 0, 1. And then down here you've got your R naught squared, sine squared, phi. So this would be the matrix. Oh man, come on, marker. This would be the matrix of this four-dimensional metric, and it's really the matrix with respect to the four-dimensional metric. If we use the natural pairing of charts from the manifolds which are being producted, is that right? Producted. Well, then the matrix is literally the direct sum of the matrices of the metrics of the manifolds being taken the product of. As you can see, it's the direct sum of the Minkowski metric and the spherical metric that we were. I guess I didn't write out the matrix of the spherical one, but if you did, that's what it looks like, right? And similarly here, if I was to, let's see, what's this one? Here I'm taking the cylinder. I guess I'll make it a homework just to drive it home. These would be easy homeworks, like find the matrix of the metric with respect to the tx theta z coordinate. Find the matrix with respect to the tx phi theta coordinate, like that. And you should be able to see that the matrix of the metric is literally the direct sum of the matrices of the metrics which are appearing for the manifolds that we're taking the product of. Anyway, so here are three genuine examples of four-dimensional spacetimes with, perhaps interesting geometry in the spatial parts, right? I mean, it's not just flat space. I don't think. Let's see here. Well, this one. I mean, 7 and 8, right? I mean, it's a sphere, right? Sphere is not flat. So this is spatially curved. Cylinder. Well, that one's interesting, right? We'll have to see about this one. It seems like a cylinder should be curved, but you may remember from elementary differential geometry, cylinder has, it's curved in one sense, right? It's curved in the extrinsic sense of its embedding in R3, but in terms of intrinsic curvature, the cylinder is not curved, because if you could imagine yourself as a two-dimensional being on a cylinder, and for all intents and purposes, a cylinder is the same as taking this sheet and doing like this, right? Right, so, anyway. So, an important and really crucial model is introduced in this section on metrics, the so-called expanding universe, and it is of course a toy model, in that the universe is a big place, and this is really just trying to capture some sort of large-scale sense of what the universe is like. So I mean, there's so many things in the universe, right? So many inhomogeneity, so many planets and solar systems, and all of those things assumably have gravitational influences on one another, and so forth and so on. And it seems like these sorts of models are ignoring all of that. But anyway, let's look at it. So it's fun to think about anyway, if nothing else, right? So if we imagine a universe which is Euclidean spatially for a moment in time, but then given a scale factor a of t, we can study the metric this ds squared is minus dt squared plus a of t squared times dx squared plus dy squared plus dc squared. You mentioned this is a special case of what's called the Robertson-Walker metric, and for physical reasons we're assuming that time is greater than 0. All right. Here's what it looks like in terms of clumsy tensor notation. And so if you look at it then, the submanifold of spacetime of fixed time, right, if we take a fixed time slice, then you've got a Euclidean metric and with a particular scale factor out front, right? And then you can do things like study a path for which the path is a path in space-time such that the coordinates, the spatial coordinates, are fixed. All right, so like that, and that's said to be a co-moving path in this context. And if you have two co-moving world lines, let's say phi 1 and phi 2, which are stuck at x1, y1, z1, and x2, y2, z2, then you can look at the distance between them at time t, and because this is, for fixed time, this is Euclidean space, right? It makes sense to look at this distance formula, I suppose, in some sense. And you can see just in your face that the distance is based on this, well, it's a scale factor, right? So in other words, the distance between these two co-moving points is, it's changing according to how the scale factor is changing, right? So these two paths are just minding their own business, staying at the same x naught, y naught, same x, y, z coordinates, and yet the distance between these x1, y1, z1 and x2, y2, z2 is expanding as space itself expands. And I think, by the way, that in this context it makes sense to say lambda. We can choose the parameter t for these paths. All right. Anyway, so Carroll shares with us here some nomenclature about these things. He says, typical scale factor has the form a of t is equal to t to the power q for some 0 less than q less than 1. He mentions in a matter-dominated universe, q is 2/3. In a radiation-dominated universe, q is 1/2. And we think of t equal to 0 as the quote-unquote Big Bang. This is really nothing to do with anything. I was just playing with a stencil with Benjamin, so if you're wondering. All right, so it's always interesting in a semi-Riemannian manifold where, in addition to just having a semi-Riemannian manifold, the coordinate that is connected, if we have a signature 1, right, that means there's one special coordinate that corresponds to eigenvalue negative, and that coordinate has to do with time, right? And time is special because time has a lot of physical import, right? Causality is, something that can't be ignored, because if you ignore it, then you find yourself with all sorts of logical paradoxes, right? Killing your grandparents, good stuff like that. So, hey, 2015 is come and gone. Where's my hoverboard? But anyway, so if we consider ds squared equals to minus dd squared plus t to the 2q, dx squared plus dy squared plus, in other words, I'm just taking a of t equals to t to the power q, and then we search for null paths. So a null path is one which would be the analog of like a light cone in Minkowski space, right? Where ds squared equals to 0. And just to keep things simple, we're going to suppose that we're fixing, freeze out y and z, so fix y and z to be, particular values. And so then you're just looking at 0 equals to minus d squared plus 2q, t to 2q dx squared, which if you solve for that, you get dx dt is equal to plus or minus t to the minus q, which then we can separate, integrate, and do some algebra, and then I'll put back in, x equal to x1 equal to x and t1 equal to t, and I'll put t0 equal to 0, ignoring the whole thing about not doing t equal to 0, because that seems to be what has been done for this formula, so whatever. So then you get this formula, which gives you that formula, which then, if you solve for t, gives you this. And here's the formula, which is given in Carroll. I think, modulo the placement of plus or minus or something like that. This is basically the formula which he gives. All right, so this is the formula for this is the formula for a null path. All right. Now, if this kind of nonchalant differential pushing jibber jabber doesn't excite you, and you want to be all formal and technical about junk, you can go over here and look at this, right? You can consider a path parameterized by lambda. You can look at the tangent vector field to the path, which gives you dx d lambda. Well, this is the tangent field, right? Dx mu d lambda, partial x mu. You can feed that. You can look at what does dt squared do to that. Well, when you plug dt squared into this, you end up with dt d lambda squared, And if you plug in the VV into dx squared, you end up with dx d lambda squared. And then, so basically, if I look at, basically plugging the vector v into the metric and assuming it's a null, if I plug the vector v into the metric and assume that it is the vector field of a null path, it leads me straight away to this equation. And then if I solve that, but I also know that dx dt times dx d lambda dt, these are equal because of the chain rule, and as such, I end up again back to where I started, which was dx dt equal to plus or minus t to the minus q. All of this just to say that it is often the case that when you use this method of differentials, if you will, sort of formal use of differentials, it often works out. See, because, I mean, yeah, dx squared wasn't really dx squared, it was dx tensor dx, right? Yet, treating it as if it was the multiplication of dx to dx and doing these formal manipulations has led us to the same point that doing the careful, evaluation of the vector field of the hypothetical curve you're looking for on the metric tensor and setting that all equal to 0 has brought you to the same place, And, I don't know, like, it's a beautiful thing about the differential notation is it is so forgiving for those who don't know what they're doing. But anyway, I often count myself among them. There are examples where that sort of nonchalant method breaks down, but it's, I don't know, some of them are kind of contrived. All right, let's go on. So, anyway, I decided to take a look-see here at q equal to 1/2 in that formula, which brought me to this. T equals to 1/4 x minus x naught squared. That's a parabola in xt space, So here's some parabolas, right? And the thing is, if you think about 2 points, right? Point 1 and point 2, these are 2 events in space-time in this expanding space-time toy model. These 2 events, right? If you track their future light cone, right? Eventually they're going to intersect, right? But if you, on the other hand, look back in time, their light cones do not intersect. See that? So like, this one tracks back to here, that one tracks back to here, but these guys, past events do not intersect, right? So the past of P1 cannot be linked to the past of P2. If you instead did this kind of picture in Minkowski space, let me indulge me for a second here. Let me add that right quick. It won't take long. So here's Minkowski space, right? Man, oh no, I don't know if I can write. So sad, I can't write next. So Minkowski space, if I take 2 points, like, P1, P2, right? And then I draw the light cones for those. What does a light cone look like in Minkowski space? Right, it's just, well, fine, I'll try to freehand it. This won't go well, but I'm going to try. That's the light cone in Minkowski space, right? For P1, the light scone, listen to me. Golly. The light cone for P2 in Minkowski space is this, right? So, of course, there's a point in the past where the light cones intersect, right? So if you go far enough back in the past, P1 and P2, they could be experiencing influence, right, from the same, event in the past, right? They're in the future. They're in the future of two different. They're in the future of this point Q. Future in the sense of being within the, on the light cone or within it for. So this is Minkowski. So the toy model expanding universe space and the Minkowski space are rather different in their stories of chronology, right? And their light cones. So light cones of P1 and P2 do not meet, and at the past, and this does not happen in Minkowski space. Light cones of separate events will intersect. All right. Now, Events such as P1 and P2 are out of causal contact because their path light cones do not intersect. And so if you, I'll tell you where this story goes and why this is in particular interesting. It's, I think this ultimately will lead to the one of the motivating factors for, you know, the introduction of inflationary cosmology. But I'm going to hold off on saying more about that until we study. There's this expanding universe model. We come back to it again in chapter 3, I think, once we know a little bit more. So I'm going to leave it for there. But this is important, that these 2 points cannot, right? They cannot be based like if there can't be a cause which is affecting both of these. All right, that's the point here. Right, whatever happens here and here, it's got to be causally disconnected. All right. So equations. So let me get on here with the rest of this. Equations 2.63 and 2.64 provide example spacetime exhibiting closed time-like curves. So what's a closed time-like curve? Well, that means the curve is always pointing in a time-like direction, and yet it comes back where it started. That's a loop in time. And so you can look at Carroll, pages 79 to 82, for some discussion of that. Or I recommend watch Interstellar. Anyway, sorry. Spoiler alert, I guess. Sorry. But actually, Interstellar is really, really worth watching if you want to sort of get some, just try to like viscerally experience what some of these relativistic effects mean for actual space travel and things like that, at least hypothetically. I mean, of course, it's a movie, so nothing's quite, believable. But anyway, so here's a picture from Carroll. He talks about a space-like surface sigma and then a connected subset of that S. And for such a connected subset, you can talk about the future domain of dependence and the past domain of dependence, and then the boundary of the past domain of dependence is the past Cauchy horizon, and the boundary of the future domain of dependence is the future Cauchy horizon. And pretty much whenever we're trying to solve problems in relativity, to be careful, we're ultimately solving partial differential equations that are subject to boundary values, and these kinds of considerations are going to enter in, if we're being careful. So I think, probably this couple pages in Carroll is something we should all revisit before we really do hard problems in relativity. It'd probably be wise. But anyway, move on here. I think we got to see the forest before we study the bark. Let's see here. So next up and last for this lecture, I want to talk about the degrees of freedom plausibility argument for locally inertial coordinates. So locally inertial coordinates were the ones for which the, what are they? So locally inertial coordinates are one for which g mu nu is eta, and the derivative of g is, the first derivatives of g are 0. All right. So these look like flat space to first order. And in chapter 3, we actually will explain how to construct such coordinates. For now, we're just going to argue that they're plausible. And for convenience, we're going to assume that our coordinate system and our transformed coordinate system are both 0 at the point P. And so, so let me explain this, the logic of what's going on here. We're starting with a perhaps arbitrary metrics without the bars, the g alpha beta, and we want the g bar mu nu to be the eta, all right? And the question is there enough flexibility in changing coordinates, right? Because in principle, if it's possible to find a coordinate system, he uses the hats, of course, I use the bars. If it's possible, is it possible to find a coordinate system that when you transform, you're originally not equal to eta g? Can you transform this to be eta in the other coordinate system? And so here's the argument. Well, yes, you can. Here's why. The argument involves some multivariate Taylor expansions. So, like in particular, the coordinates can be expanded in the transformed coordinates like so, and likewise the coordinates, the metric can be expanded in the derivatives of the transform metric can be written in terms of the original metric in terms of this expansion here, like so. So these are expanding one in terms of the other. Let's just say that briefly. And he schematically. In other words, if you wanted to, you could add the indices here to make it more correct, like what I have in blue above. But I'm perfectly content to just look at it like this. This is just a counting argument, so don't spend too much time on it. All right. Although I will tell you, theoretical physicists can do quite a lot with counting arguments and degrees of freedom. Like, you'd be surprised. So order zero, we want. Okay, so it's let's see here how to say this. We need it to be symmetric. So 10 components fixes us. You need 10 separate equations to fix 10 separate pieces of data to fix a symmetric two-index tensor. So on the other hand, you've got the freedom to adjust the Jacobian matrix of the coordinate transformation. That's got 4 free indices, so there's 16 degrees of freedom there. So you get 10. You use 10 of them to put the basically to put the g equal to eta, and then there's 6 degrees of freedom left over. But these are just the degrees of freedom for the Lorentz group, so they leave the eta, the g bar unchanged. He says that's order 0. Order 1. And I'm just telling you what he says. I'm not trying to justify this method of counting as a rigorous formal mathematical procedure. I'm just sharing with you what Carroll says as best as I can, which maybe isn't that great, but it is what it is. All right, let's go on with it. I mean, the conclusion here is interesting. So order 1, if we look at order 1, all right, so like, let's see here. So just to recap here, order 0 is just looking at this relative to that, okay? So you got your g bar over here, and you got your partial x bar g over here. And the point is that you got 16 things to play with here, but you got 10 things that you need to fix over there. So 16 versus 10, 16 is definitely enough to put that into order, and the 6 that are left over aren't gonna mess up the 10 you already used, because that's just the Lorentz group. All right. Next up, you've got this derivative of g bar matching this stuff over here, right? Now you've already used up partial x bar in the previous step, so you don't have any freedom over that anymore, because you already fixed your partial x bar in fixing up the g bar. But now you got your partial squared x bar to play with. All right. So how's that go? Well, first of all, you got to fix your partial bar g bar. That's with indices like this. Now here, this is 10 independent things, because remember the symmetric is symmetric. So while it might appear there are 16 things here, because of the necessary symmetry of the indices, it turns out that, like G12 is G21, G13 is G31, G14 is G41, G23 is G32, and so forth. So it reduces by, there's just 10 independent components for a tensor in 4 dimensions with 2 free indices that are symmetric. So there's 10 components there. And the partial bar alpha, that's got 4. So 4 times 10, these are independent choices, so that's 40 components. You got 40 components to put into line here, right? But on the right-hand side, over here, you get this partial squared x, partial x bar term. Now, since the derivatives commute by the Fubini or Clairaut's rule, whatever you want to call it, that's symmetric. So it's a symmetric with two indices and 4 dimensions. So that's 10 things, but the mu is free. So that's 4 times 10. Again, you get 40 degrees of freedom. So you got 40 degrees of freedom here. You got 40 degrees of freedom here. So basically, think of it this way: you got 40 equations and 40 unknowns. So as long as those are genuinely independent equations, then voila, you can solve it, right? And so we can make that be 0 if we want. All right. And great. So that means so far we've basically argued the plausibility of creating the locally inertial coordinates. Now he's just going to go the next step and explain why that's as far as you can go. All right, and what fails at order 2, which is actually kind of the more interesting part here in some sense, because at order 2, you're trying to match this partial g term with all of this, right? And the new things here that you haven't already fixed from your previous steps are the partial cubed x, partial x bar, partial x bar, partial x bar term, right? And so this and this, so you got 2 symmetric indices and another 2 symmetric indices. So to pin this down, to fix this, you need 100 equations, basically. You need 100 degrees. This has 100 degrees of freedom. To fix this, you need 100 equations. But you don't have that much, because on the other side, you've just got this partial cubed business right here. And if you study a completely symmetric rank 3, a completely symmetric tensor in 3 indices, it turns out that there are 20 of them. Now that's not obvious. Why is it there's 20 degrees of freedom if you have three indices in 4 dimensions which are completely symmetric? It's not obvious why that's 20. All right, but it is. I probably should make that a homework question. Anyway, and then of course mu is free, so that gives you 4 times 20, which is 80. Well, 80 is not 100, so you're missing 20 degrees of freedom to fix that. And so you cannot just glibly set the second derivative of the metric equal to 0. Now here's the cool part, which we'll hopefully start to understand next lecture, which is that the missing 20 degrees of freedom, which prevent setting second derivatives of the metric to 0, those are accounted for actually in the Riemann tensor. So the Riemann tensor is somehow, whatever that thing is, it is making quantifiable the obstruction to setting second derivatives of the metric to be 0. In other words, we're ultimately going to see that non-trivial Riemann tensor is tantamount to your space not being flat. See, in a flat space, the metric tensor is just the Kronecker delta, and you can differentiate that thing all day long and you just get 0, right? So when your space is more interesting, maybe that doesn't happen. And exactly how that doesn't happen is somehow encapsulated in this Riemann tensor. And this Riemann tensor, which is a 4-index beast, is tied together with a number of other interesting tensors, all of which somehow center around the question of what is curvature, and how is curvature an obstruction to your space being flat. So anyway, hey, that's a really fuzzy and totally vague preview of where we're going. But folks, that's about all I have to say about Chapter 2 in Carroll, so sorry if this was a little bit too quick, but I have yet to find a way to do shadow. If I could make a shadow clone of myself, maybe I could do more of these, I guess. But anyway, thanks guys.